Welcome to the ANSYS AIM tutorials. In this presentation, I'd like to show you how to determine the airflow around the body of a model car, how to determine the pressure distribution that ensues, and then, building on that, how to determine the structural deformation. What we shall be employing for this purpose is the process of fluid-structure interaction, which links together flow simulation and structural mechanical analysis. Once AIM has been started up, the particular template we want to select is the Fluid Structure Interaction template. In the next step, we determine whether our geometry only contains a solid body or whether it also contains the flow volume. In this case, the latter is the case. And in the next step, we deactivate the detection of contacts. But we do specify that we want to configure the geometry, and the next step is to then import the geometry. The simulation process is then generated by ANSYS AIM. Firstly, the fluid flow analysis, and then the structural analysis. The first step is to configure the fluid structure analysis. Our geometry contains two aspects. On the one hand, we have the solid body, and then we also have the fluid volume of the surrounding air. For the purposes of the fluid flow analysis, we suppress the solid body, i.e. we select this body and we define how it is to be suppressed. With the configuration completed, the body is suppressed and the volume of air remains. We then mesh this volume of air. We can either employ global mesh settings via the slider, or we can define the global settings manually, i.e. we define minimum element sizes, maximum face sizes, and maximum element sizes in volumes, and also a growth rate, by which we mean the transition from small elements to large elements. In the next step, we define an inflation layer, where we can solve boundary layers with greater precision. We want to carry out this more precise analysis, above all in the area of the transition between the solid body and the airflow, i.e. we select the surface of the solid body and specify how many elements are to be modelled within these boundary layers, 15 in this case. We mesh the geometry and obtain the individual cells, and we can check whether the mesh corresponds to our expectations. The next step is to define the airflow simulation. We firstly define the material. The air has been predefined, and we want to confirm this definition. AIM directs us to the next definition of the inlet. We select the geometry and specify that we want to use an airflow velocity of 5 meters a second at the inlet. In a similar fashion, we specify a pressure of 0 megapascals at the outlet on the opposite side, i.e. we select the option to define an outlet, assign the geometry, and specify a pressure of 0 pascals. We also need to define a symmetry boundary condition. So we select the surface across which we want the symmetry to arise, assign this surface as the location, and thereby complete definition of the symmetry. The final step in defining the boundary conditions is to define the wall boundary condition. When this is selected, any geometries that have as yet not been assigned are automatically selected and assigned. This completes the definition of our model, and we can begin the analysis. We can see the analysis progressing in real time, enabling us to estimate how long the analysis will take. Once the results have been calculated, we can visualize the default result. Firstly, the airflow velocity. The default value of 100 arrows used in this visualization is too rough, so we're going to refine the results and also define some additional results, such as portrayal of the pressure distribution. We therefore select the outer surfaces of our simulation model, and we define pressure as the result to be used for the visualization. And when we refresh the results, the pressure distribution is then illustrated. We can see the high pressure region here at the front, and we can see the negative pressure that occurs in the top surface region. We can also define results in the form of streamlines. These streamlines require a starting location. In this case, we're defining the inlet as the starting location. We specify how many streamlines we want to generate, and then we see how these streamlines arise between the inlet and the outlet. In the area behind the vehicle, you can also see a pressure region being created here. In order to visualize magnitudes, we generate another result, a contour result, and we select the streamlines as the location for the visualization. And then we select the specific magnitude we want to see, in this case, the flow velocity. Having refreshed the result, we see the streamlines colored in accordance with velocity. So we see high velocities above the vehicle, and in the area of the pressure region, correspondingly lower velocities. Following the flow simulation, the structural deformations need to be calculated on the basis of the pressure distribution. This pressure distribution is uneven. So here we have another image. Different pressures arise in different places, and this pressure distribution should be transferred to the structural model for the purpose of calculating structural deformation, in order to obtain the correct and precise load. So we now transfer over to the structural analysis and configure the model such that the flow volume or air volume is suppressed. And we then specify the mesh for the structural analysis. So here we're using a global mesh stream. We generate a refined global mesh density, and using this mesh, we begin to define the structural requirements. This is firstly a question of defining the material. So we select polyethylene from the material library and assign it, and we can then also verify the properties of this material. In the next step, we define the mechanical boundary conditions, and also the related symmetry conditions for the surface on which the pattern of symmetry is generated, i.e. the center of the car. We select this surface and specify that the translation is fixed along the x-axis. All other translations are free. In addition to this, we also require a support on the underside. So we select the corresponding surface, and we here add a support boundary condition. In the next step, we define the translation of the pressure distribution, which is a fluid flow analysis. We define which surfaces the pressure is to be applied to. In this case, it'll be the outer surfaces of our vehicle. We select them and assign them to this coupling. It's not a problem if the structural model and the fluid-based mesh don't match, as the mesh is generated automatically. We're starting the analysis, and once the analysis is complete, we can also update the structural mechanical results. The visualization of the mechanical deformation enables us to see how the solid body is deformed on its upper surface as a result of this pressure distribution. So you can see that ANSYS AIM provides for integrated observation of flow mechanics and structural mechanics.